Here's a third problem in this mini-series related to finding the shear force and bending moment diagrams for different loading scenarios. And again, this is the kind of problem that you might encounter as a first-year engineering student. So if you'd like to see anything similar to this, or if you have any questions related to something else, let me know in the comments. So in this problem, we're dealing with a beam and we have two distributed loads. So we have the first one, which is called W naught, which is acting from the left hand side until the halfway point, and then we have 2W naught, which is acting from the halfway point all the way to the right hand side. So as usual, what I'll do is I'll draw the free body diagram of the beam, and then we're going to try to find the reaction forces, which is what I would recommend to start with. So we have the halfway point being somewhere here, and then we've got W naught until the halfway point, like this. And then from that point onwards, we have 2W naught, like that. Okay? Right. Then afterwards, we're going to draw the reaction forces. So first of all, we have point A. So where point A is, we have a simple support, right? And the simple support can withstand a horizontal and a vertical reaction force, but because there's no other horizontal reaction force in the problem, um, the horizontal component will be 0. So we just have a vertical component at A, which we call RA, and then B is just a roller, so we have a vertical reaction force anyway, so that's RA and RB. And now we're going to try to find what the two reaction forces are. And to do that, we're going to first add up the forces in the y direction, and the sum of forces in the y direction is going to be 0, and then upwards is going to be my positive direction. And we have two forces acting up, which is RA, and then we have RB. And then we have two other, well, we have the distributed loads. So the length of the beam is given to us as L, which means that we have L over 2 until this point, and then we have L over 2 until this point. So the force due to the first distributed load, due to this one, is going to be minus because it's acting downwards, and it's minus W naught times L over 2. And then we have minus the other one, so 2W naught times L over 2. So it's just the distributed load times the length, because it's just a uniformly distributed load. Then I'm gonna rearrange and say that RA plus RB equals, and then we have 1/2 W naught L, and then you can see that the 2's cancel. So this is going to be just plus W naught L, which, so 1/2 plus 1, that's going to be 3/2 W naught times L. So the first equation that we have, which is not enough, is RA plus RB is equal to 3 over 2 W naught L. So we need one more thing, and as usual, we use the fact that there is rotational equilibrium as well. So I'm gonna take moments about point A. You can take moments about B if you want, or about the middle, or about any other point. But I'll take moments about A, and I'll say that the sum of moments about A is equal to 0, because that's what balance means, and then counterclockwise, moments are positive. So RA doesn't produce a moment about A, because it's acting through this imaginary hinge. So we have our RB, which does produce a moment, and it produces a counterclockwise moment, which is positive. So RB times L on one hand. And then we have the two distributed loads, which produce moments as well. So W naught is gonna have a corresponding force of minus W naught L over 2. So that's just the force, right? So this distributed load W naught produces a net force which is acting like halfway, okay? Halfway along L over 2, which means that the moment arm of this force is going to be half of L over 2, which is L over 4. So that is multiplied by L over 4. So that's basically the force, and L over 4 is the moment arm. And we do the same thing with this one. So 2W naught will generate a net force acting halfway along the right hand side of the beam, along the right half of the beam. And the moment arm with respect to point A is going to be this, which is L over 2 plus L over 4, which is 3L over 4. Okay, so we have minus, because again, 2W naught produces a clockwise moment. So 2W naught times L over 2, that's the force. And we multiply that by the moment arm, which is 3L over 4, and that will equal 0. Then, just to simplify things, I'm going to cancel an L from everywhere, and I think I can cancel this 2 with this 2, and that's about it. So we have RB. So I'm going to leave RB on the left and move everything to the right. So we have RB will equal W naught L over 8 plus, and then we have 3 W naught L over 4. I think I picked everything up, so yeah, that's it. And then we're gonna multiply this fraction by 2 top and bottom to have the same denominator everywhere. So this is W naught L plus 6 W naught L over 8, right? Which is 7 over 8 W naught L. So that's the reaction force at B, which means that we found this one. So to find RA, we can just use this equation here and subtract. So we have 3 halves W naught L minus 7 over 8 W naught L. And you know what? I think I'll just factorize W naught L because it's in both terms. So this is 3 over 2 minus 7 over 8, which is, if we amplify this by 4, this is going to be W naught L. So we have 12 minus 7, so that's going to be 5 over 8. So I'm going to write the reaction forces here. So we have RA on one hand, which is 5 over 8 W naught L, and then we have RB, which is 7 over 8 W naught L. And that's it. So we have that RB is greater than RA, and from an intuitive point of view, this actually does make sense because most of the load is focused on the right hand side of the beam towards B, which makes sense for B to take most of the reaction. So now that we found this, now that we found the two reaction forces, let's try to find the internal shear force and bending moment. So to do this, we're gonna have to take an arbitrary length. We're gonna first have to do that imaginary cross section, which first I'm gonna do it somewhere here, and then I'm gonna do it somewhere here, and we're gonna expose the shear force and the bending moment, and then plot them afterwards. So let's first take our arbitrary x somewhere between L over 2 and 0. So again, I'm gonna take a section like this, and I'm gonna draw the free body diagram only of that section, right? So this has a length of x, and then I have RA here. Then I know I have a distributed load, which is just W naught like this, and then on the face that's been cut, I have a shear force and I have a bending moment. So let's find the shear force and then let's find the bending moment. So this is, I'm going to put a 1 here because I'm just talking about the first section, and then I'll do the same thing for the second section. So we have, again, sum of forces in the y direction equals 0. So we've got RA, which is up. We have minus W naught times x, which is down, and then we have s, which is also down due to the convention. So then my shear force is Ra minus W naught times x. Okay, so I'll take this, I'll move this here, and this will give us that the shear force is going to equal Ra. So Ra was 5 over 8 W naught L, and this is minus W naught X, where X, remember, is our variable, is the thing that's changing between 0 and L over 2. So the shear force, I'll write S of X, shear force as a function of X, is going to be W naught, and then I just have 5 over 8 L minus X. Okay, so this actually allows us to find the shear force at the middle. So at the upper bound for X rather, which is L over 2. So let's do that just to see what it is. So this is W naught, and then we have 5 over 8L minus, and then we have L over 2. So S of L over 2 is W naught, and then 5 over 8L, or I should say 5L minus 4L over 8. So the shear force at the center will therefore be 1 over 8 W naught L, which will allow us to plot exactly how the straight line is going to look, because in case you haven't figured out, the shear force will be a straight line, right? It's a first order function because it just depends on X, and of course this is a constant. Right, let's then find the moment. So for a moment, we're going to do the same thing as for the um, as when we found the reaction forces. So sum of moments, and I'm going to take moments about this point, which is on the cut face, and I'm going to call that point P. So sum of moments about point P will be equal to 0. So let's see what we have. First, we have the moment M, the unknown bending moment. Then we have, well, the shear force doesn't produce a moment about P. Then we have the reaction at A, which produces a clockwise moment. So that's minus Ra times X, because X is the moment arm. And then we have the counterclockwise moment due to W naught, which is plus W naught X. That's the force. And the moment arm, as usual, it's just half of that, which is X over 2. So that is equal to 0. So the moment will be Rax. So Ra, again, we said it's 5 over 8 W naught Lx minus, and this is 1/2 W naught X squared. So if you want, which I think I'll do that, I'll say that Mx, M as a function of X, will be W naught over 2 brackets. So I'm factorizing W naught over 2. And this is 5 over 4 L times X minus, and then we just have X squared. So let's try to find the moment, and let's try to find the moment at the middle point and see how much that is going to be. So M of L over 2 will be W naught over 2, and then we have 5 over 4, and then we have L times L over 2 minus L squared over 4. So this is going to be equal to W naught over 2, and then we have, so in the brackets, we can't actually simplify anything, but we have 5 over 8, and then it's 5 over 8 L squared minus L squared over 4. So M at the middle is going to be equal to W naught over 2, and then we can amplify this by 2, so that's 3 over 8 if I'm not mistaken, so times 3 over 8 W naught Actually, there won't be any more W naught at this point. It will just be L squared. So this should be 3 over 16 W naught L squared, like this. And that is the moment at the middle point of the beam. Okay, so this is going to be useful when we plot, but we're going to do that later. Until then, we have to also find the shear force and the bending moment here somewhere. So I'm gonna take another cross section after the halfway point and draw the free body diagram for that. So we have the beam, we have the distributed load acting until the halfway point of the beam, and then from this point until the end of X, we have 2W naught. So remember, this is not the full length of the beam, this is just X. And in this case, X is going to be between L and L over 2. So we have a reaction force here, which is RA. We have a shear force here, which is S, and we have a moment, a bending moment here, which is M, right? So this is the halfway point. So this was L over 2, which means that this remaining bit is X minus L over 2. Okay? So let's find the shear force. So we have sum of forces in the y direction is equal to 0, vertical is positive, and we have RA minus, so now we have two distributed loads. We have this one, which is W naught, we have this one, which is 2W naught. So W naught is acting along a length of L over 2, and 2W naught is acting along this remaining length of X minus L over 2. And then we have minus S, and this is equal to 0. So let's rearrange and see what we get. So the shear force is equal to RA minus W naught L over 2. So all I'm doing now is I'm moving the shear force to the other side. So we have RA minus W naught L over 2, and then minus 2W naught, and then the remaining is X minus L over 2, like this. So the shear force is RA was 5 over 8 W naught L minus 1/2 W naught L minus 2W naught X, and then this is going to be plus W naught L. So we can actually combine those two into one. So, well, we can combine actually those three. So the shear force as a function of X is going to be, let's see, so W naught L times, we have 5 over 8, and this is 1 minus 1/2, which is plus 1/2, and then minus 2W naught X. So I amplify this by 4, we have W naught L multiplied by 5 plus 4, so that's going to be 9 over 8 minus 2 W naught X. So that's W naught brackets 9 over 8 L minus 2X. So that's it. That's what the shear force is. So you will notice if you replace X with L over 2 that you should get exactly the same shear force as the previous one. So let's actually do that and convince ourselves. So this is going to be 9 over 8L minus 2 times L over 2, which is just L. So that is just 1 over 8 W naught L. So the shear force at the middle is 1 over 8 W naught L, which should be the same as this, which is the shear force in the middle using the previous half of the beam. And I think for mathematical accuracy, I should do this here as well. Okay, there is only one more thing to do, which is finding the bending moment. But before that, we have the shear force everywhere, so I'm gonna plot it. So I'll do that here. So just to do something new in the meantime. rather than just writing equations of equilibrium. So I'll write X, I'll write the shear force, and then we have the length of the beam here, and this is L over 2. So we know that the shear force at the beginning is given by this equation. So this is the shear force for the first half of the beam, for the left half of the beam. So if we want the starting shear force, we just replace x with 0, right? So we replace x with 0, we get the y-intercept, which is 5 over 8 W naught L, which is somewhere here. So that's 5 over 8 W naught L. So that's the first point. Then we know that this decreases to 5 times less that, because at half L we get 1 over 8 W naught L. So we have this value 1 over 8 W naught L, which occurs at L over 2. So the first part, we have the shear force diagram looking like this. And then for the other part, we have the shear force looking like this, looking like this. Okay, so we know it starts from this point. So it starts from this point here, but then how does it go? So to figure that out, we're going to find another point, which is going to be at L. So S of L will be W naught, and then we have 9 over 8L minus, and this is 2 times X. X will be L, so minus 2L, which should be a negative value. So we have W naught, and then this should be, if I amplify this with an 8, this should be 9 minus 16, which should be minus 7 over 8L, which is the same as the reaction force. Well, the same absolute value as the reaction force that we got. So that's that. So minus 7 over 8 should be somewhere here. So this is, if this is 5, I'm trying to draw it to scale as much as I can. So somewhere here is going to be minus 7 over 8 W naught L, which happens here like that. So it's still a straight line, but it will have a different slope like that. So that's the shear force diagram. So that's the shear force diagram, which is basically just two straight lines with different slopes joined together. And for the bending moment diagram, which we'll do after we find the bending moment for the right half of the beam, in that case you'll have two parabolas which are joined together. So let's have a look. So for the bending moment, we have sum of moments is equal to 0, and let's see what we get. So first we have M, which is counterclockwise. Then we have RA, which produces a clockwise moment, so that's going to be minus RA times X. Then we have the two green ones. So we have W naught, which is producing a counterclockwise moment. So we have W naught L over 2, which is the force. And now we have to figure out what the moment arm is. So the equivalent, the resultant force is here, which is essentially at L over 4. So you have L over 4 here. So the moment arm is going to be L over 4 plus this. So it's literally from here to here, right? Which is L over 4 plus X. So let's write it like this for a bit. Which is X minus L over 4. So X minus L over 4 is the moment arm. X minus L over 4. And then we have the other one, the 2W naught, which creates counterclockwise moment as well. So that's 2 plus 2w naught multiplied by the length x minus L over 2. So x minus L over 2. And you can check that the moment arm is x minus L over 2 squared. And the whole thing is equal to 0. So the moment will be 5 over 8 W naught L times X, because that's the reaction force. So now I'm moving everything to the other side. So this will be minus W naught L over 2 X minus L over 4. And then we have, we can actually cancel out this 2 with this 2. And then we have minus W naught and then X minus L over 2 squared. So at this point, I would actually try to expand some brackets. So this is minus W naught, and then we have L over 2x plus W naught, and then we have L squared over 8. And then minus W naught, and then this bracket will become x squared minus x times L plus L squared over 4. Okay? So now I'm gonna try to group the terms together to make like a proper quadratic, to make a nicely looking quadratic. So let's first take the x squared term, which is just 1. So we have minus w naught x squared, which is this one. So we start with that. Then we have the one with L and X. So we have this one, we have this one, and we also have this one. So I'm going to put some brackets. So plus 5 over 8 W naught LX minus 1 half W naught LX. And then that should be plus W naught LX. And finally, we have the L squared term, which is here and here. So we have, I'll try to write that straight away. So we have 1 over 8 minus 1 over 4. So we have 1 over 8 minus 1 over 4, which should be equal to minus 1 over 8. Okay, so we have minus 1 over 8 W naught L squared. Now this looks like it's pretty long, but we're going to simplify that middle term and get something a bit more nice at the end. So we have that the bending moment will be equal to minus W naught X squared. Okay, so with this one, just to see what's happening, I'll just I'll factorize W naught L and X. And in the brackets, we're going to have 5 over 8 minus a half, and then just plus 1. And then this is, again, minus 1 over 8 W naught L squared, like this. So in this bracket, we have, I can amplify this with 4 and this with 8. So we have the moment is minus W naught X squared plus W naught LX. And then we have 5 minus 4 plus 8 over 8 minus 1 over 8 W naught L squared. So I'm trying to keep track of everything. So the moment as a function of x will be minus W naught X squared plus W naught LX. So this is 5 minus 4, which is 1. 1 plus 8 is 9, so this is going to be 9 over 8. So I'll put that 9 over 8 in front, like that, and then minus 1 over 8 W naught L squared. And that's it. That's the moment. And to make sure that, well, to do a quick check, I'm going to try to find the moment at L. And that should be 0 because there shouldn't be any moment on either end of the beam because this is not a cantilever beam, it's just simply supported. So we have minus W naught L squared plus 9 over 8 W naught L times L, so L squared minus 1 over 8 W naught L squared, which is, so we have -1 over 8, which is -9 over 8, so this will be 0, which is fine. I would also be tempted to find where exactly the maximum will be in this case. So to find the maximum moment, to find the location of the maximum moment, I'm going to find the x location, which is minus b over 2a from the quadratic formula. So this will be minus. B is just 9 over 8 W naught L, and 2A is just 2 times minus W naught. So this is like that. W naughts cancel out. So this is 9 over 16L, which is slightly more than half, I would say. So 8 over 16 is half, 9 over 16 is just 1/16 more than half. So let's try to plot this. And that's going to be the end of everything. So we have bending moment, we have x, and then we have half the length, and then we have L here as well. Okay, so first I'm gonna try plotting the bending moment for the left-hand side of the beam, which is equal to this. So we start at 0 and we end up at this value in the middle. So that's 3 over 16 W naught L squared. So 3 over 16 W naught L squared, which is here. Now I would also try to find where the maximum occurs in this case. So if I do minus b over 2a, that will be, let's see, so we have minus, my b value is 5 over 4L, and my 2a is going to be, well, minus 2. So it's going to be like this, which is 5 over 8L. So the peak doesn't actually happen in this, in this first half, because it would be something like this kind of, but this is just the first part of the parabola essentially. And then for the other half, we have another parabola, and that parabola is going to look something like this, I would say. Right, with a maximum occurring somewhere here. So this is where the maximum bending moment occurs, so this M max. And this also corresponds to the place where you have zero shear stress in the beam. So that's the shear force diagram, that's the bending moment diagram, and that's the end of the question.